Okay, so Physics Summer 2018. Let's have a little look at the first question then. So explaining why friction causes students to become charged. Two key points we're looking for then: transfer of electrons. You can't talk about any positive charges, so you'd lose the mark for that if you said something that contradicts the electrons. The second mark is for then saying you're going from the carpet to the students, so that'd probably be a big improvement for a good chunk of the people sitting this one. Part 2, draw 3 more arrows. The key thing that you should know about the electric field is all the arrows are going to be pointing towards the centre of the sphere, and it says to draw 3 more arrows, so we're looking at adding 3 more in, with them all directing in. So if you did one on the right, it would point from the right to the left. If you did one from the left, it would point from the left to the right. It'd all just be coming in like a kind of like a sunshine in reverse, rather than rays going outwards. It'd all be coming in. For 1.3, the negatively charged student touches the metal tap and receives an electric shock. Whenever you're looking at a charge flowing like that, you can start off by saying the first point is there's going to be a voltage, or there's going to be a potential difference between the two of them. So just like when you see a Van de Graaff in class, when it charges up, it generates quite a large potential difference. That's what's needed to create the spark. So the second mark would then be saying about what's happening there. The spark is the electrons being transferred. So the key thing there is to say that you've got electrons moving. The third mark then being description of where it's going to. So the electrons are moving to Earth, or they're being grounded. So you say the electrons are going through to the tap to be earthed because there's a potential difference. That'd be 3 marks in one sentence. For question 1.4, the last bit on this one, why have we got copper wires inside the carpet? So the effect would be to allow the carpet to conduct electricity or to lower its resistance. That would be the first mark. The second mark would be then what the outcome of that was. If there's no resistance to it, then we're not going to be able to build up a static charge. Any charge you attempt to build up will flow away, so you just won't get static electricity at all. And on to question 2. Let's have a quick look. So we're looking at a count rate for this rock. So it's 819 counts in 60 seconds. So to find out what it is in 1 second, it's 819 divided by 60. 819 divided by 60 comes out at 13.65. It says the background radiation count is 0.30, so we have to account for that. So we take that away from it, because whether we've got this activity there or not, that 0.30 is going to be there. So actually it's only 13.35, which is from this source. If you didn't take that bit away, then you'd still be able to get 2 of the marks, as it says over here. Part 2, when we're looking at calculating the activity in the kitchen worktop, nice and straightforward. 1 kilogram of granite would do 1,250 becquerels. We've got 180 kilograms, is literally timesing the 2 together. So a mark for writing out the numbers, and then a second mark for resolving it. The answer is 225,000. Nice and easy, 2 marks there. So 2.3, we've got, continuing on the theme of the question, could this radioactivity in the worktop be dangerous? So it says that the granite worktop is giving out 0.003 millisieverts per day. And notice that all these ones here are talking about a year. So if we've got 100 in a year, we're looking at the potential that we might get cancer. So first of all, we get that 0.003 per day, and change that into years by doing 0.003 times 365. That should give you a yearly dose of 1.095 millisieverts. So that's the first mark there. Second mark then for is explaining if that is an issue or not. So 1 is going to be significant less, 100 times less than the lowest dose, which causes cancer, according to our evidence. So you'd be saying the yearly dose is 1.095, and that is significantly below the danger threshold, so this person would be nice and safe. For 2.4, last one in this section, the slightly amusing suggestion that we should not measure radiation in becquerels, we should measure them in banana equivalent doses, as in the same amount of radiation that you get from a banana. Why might this be useful for the public? It's the same thing for why units are easier for people to understand instead of kilowatt hours when you're measuring electricity. It just sounds easy. So if you're saying it's going to be the equivalent of eating one banana, people can visualize that. So if you have a look at the mark scheme, people are able to compare the radiation risk of a banana or a dose to whatever it is that we're talking about, whether it's worktops or nuclear power stations or nuclear testing. So flying on to question 3, this one should be nice and familiar to you. We've got from the key assess practical the resistance of the wire setup. In this question here we're asked to add in the ammeter and voltmeter. First easy mark, no matter where you've put the ammeter and voltmeter, if you drew a circle with a capital A in it and a circle with a capital V in it for the voltmeter and the ammeter, then you've got the first mark. Second mark, let's look at the voltmeter. So voltmeters are measuring the voltage or the potential difference. So the reason it's important to remember it's potential difference, it measures the voltage change across a component. So you'd need to have a line coming from the left of the wire, coming out and going through your voltmeter and then going back to the right. It doesn't matter if it comes down below it or goes above it, but that would be connecting it in parallel and scoring you the second mark. The third mark is for the ammeter, which measures the current. Just like if you're measuring the current of a river, you would need to put your hand into a river to measure the flow of the electricity, and an ammeter does a very similar sort of thing. It's measuring the flow of the electricity, so it needs to go in it. So anywhere within the loop, if you added a circle and put an A on it, that would be the correct place to put it. On to the 6 mark question. So we're looking at how we'd use that equipment to carry out the investigation. Have a quick look at the mark scheme over here on the right for some of the key points that I'm talking about. So the first thing that we need to do is we'd need to measure the length of the wire, and then we'd need to vary the length of it. So the picture there in a second shows you can vary the length by just moving the crocodile clips further along the wire to make the wire that the electricity is running through longer. And that measurement would need to be recorded in a suitable table. Every time you've changed the length of the wire, you'd need to make a note of the current and the potential difference, that's the voltage, using an ammeter and a voltmeter. And we'd expect that you'd do repeat readings, at least 3, so that you could work out an average current and an average potential difference. You can then calculate the resistance for each of the wires. To do that, you get the resistance by getting the potential difference, the voltage, and dividing it by the current. You'd then be able to interpret your results, which is where a lot of people don't get the marks where people otherwise would have for nice simple things like talking about measuring the current and voltage. So plotting a graph of resistance against length would give you a chance to see if there's any pattern, which obviously there will be. A longer wire would have a higher resistance. The hazard in this one is we've got the electricity flowing along through the wire with minimal resistance, so you're going to get a high current flowing. So the high current is going to mean that the wire gets very, very hot and starts overheating, which may cause burns. So what you'd be looking at doing ideally is using really low currents. One of the things it does go on to suggest is things like only turn the device on when you're taking your reading and turn it off straight away. And it does tell you in a second why to do that. It doesn't actually count as any of the marks in this bit. So 6 marks in this would be for you doing this as a nice logical method where you got a good order, good use of key vocabulary, capital letters, full stops, all the way down to 1 or 2 marks, which is where we're looking at some of the ideas, but no real overall order or pattern to what it is he's suggesting that we do. For part 3, switching off the circuit between readings would have improved the accuracy. So the reason that this is because the longer that this is on, with the more current flowing through it, we're going to have a higher temperature in the wire. So as you get a higher temperature, the atoms of the wire, or the cations, they're going to start vibrating more, which means there's more resistance, more things in the way of the electrons flowing along. So that is why we're choosing the option temperature of the wire would not change. So if we keep turning it off, the wire's not on long enough to heat up, so we won't have the temperature affecting the outcome. If we left it on all the time, it'd get really hot, and that would then increase the resistance, which is not something that we're looking at changing in. So as I mentioned earlier, this is the suggestion they've got as 2 alternative ways of changing the measurement, and it's a nice picture here showing you. Here you've got the crocodile clip, which has got quite a broad nose, and it can be a little bit ambiguous as to which point you're measuring to, so you might get an error in your measurement. With your jockey here, it's much sharper, to the point, and you can measure on your ruler to exactly which point you think it is that you're measuring the distance. So in that, if you did your results 3 times and then you averaged it, you would be getting something which is closer to the correct average. That means your accuracy would be improving and you'd have a higher accuracy, which is the top box. Resolution is about the measurement between the 2 smallest points. So in a microscope, it would be the smallest distance that you could measure between points on a magnification. And here, obviously, it's going to be a higher resolution because you can measure to the closest millimeter rather than to the closest couple of millimeters. So we're looking at a higher resolution, which is going to be this third from the bottom one as well. Okay, question 3 done. Ready for question 4. So, question 4. So we're linking into energy and forces here, obviously, because we've got a bike. As the cyclist rides along the road, the something energy stored in the cyclist's body decreases. A little bit naughty in that they've not given you any keywords here, but you should know about the different energy types. It's not going to be thermal energy that's decreasing. It's not going to be nuclear. It's not going to be elastic. It's the chemical energy that's going to be from his body, from his energy stores. The speed of the cyclist is constant, so the work done to keep that constant speed must be equal to the work done against the air resistance. For question 4.2, the equation that links power, time and the work done. So this mark scheme here suggests power is work done divided by the time. It really doesn't matter which way round you get it, so as long as the terms work out the same way. So if you had work done equals power times by time, that would be the same thing as well, just in a slightly different organisation. So that would also score you the mark if you did that. If you're going to use the letters, make sure that they're the correct letters for the same thing that we'd write in our book or from the answer sheet. In this case, it's quite sensible: P for power, W for work, and T for time. But I'd suggest that you write the words just so that you don't get anything wrong with some weird or shortened letters. For the calculation, it's just a case of using that formula. If you didn't know it, obviously it was a little bit harder for you. So look at the way the marks are structured for this. The first mark is for substituting your numbers into the formula. Before you do anything where you can make a mistake, make sure you do that. And then we've got a very simple form of algebra to solve out. If 200 is the answer when you get W and divide it by 1800, how would you find out what W is? So you'd get that 200, times it back by 1800, and then that would give you an answer of 360,000 joules. And that should be not surprising for you, because joules are a really small amount. So the work done for the 1,800 seconds, 360,000 joules is a pretty sensible sort of number to get. For question 4.4, calculate the percentage increase in speed of the cyclist when we're going from 200 watts to 300 watts. So we need the graph for this one. Cheeky, we scroll back up. We look at 200 watts and we go up. It's 1 square below the 10. And if you look at the scale, 2 squares is going to be worth 1. So that would be 9.5. And then 300 is 2 squares above the 10. So that's going to be a whole one above 10. That's going to be 11. So the difference is going to be from 11 to 9.5 to 11, which is an increase in 1.5 meters per second. That's this bit of the mark scheme here, and that gives you 1 mark. The second part then is for working out that increase as a percentage. So if you're looking again at the calculation here, that is 1.5 out of a total of 9.5 times by 100. It's the same way as you'd work out as an answer in a test. That should give you 15.8%. The last one in the question says the maximum speed is 14 meters per second on the flat. So what's the maximum? What's going to happen to the maximum speed if we're going uphill? 3 key points here. So first easy mark, the speed is going to be lower. Excuse me. That's because, and here you've got a couple of points of where you can get the marks. The maximum power output is constant, is fixed, so that's not going to change. And the final mark is for saying either that the work done is now being split, so there's some against gravity as well, or I think you'd be more likely to say that as well as the kinetic energy store, that the cyclist is putting smooth air energy into the gravitational potential energy store. Or if you didn't say that, it's best to do the correction now for me then, please. But you're super excited and ready for question 5. Let's go for it. Nice easy start. You'll notice that with the structure of the questions, as you're going through the exam paper, the questions are getting harder, but the start of each question is the easiest one. So if you are struggling in the exams, make sure that you don't just get stuck on one, you do keep moving through. Go to the easy questions at the start of each question, bag those easy marks. So this one, keywords given. The current through the ohmic conductor is directly proportional to the potential difference. You'd be able to use voltage or PD there, but the word in the box is potential difference, provided that the temperature remains constant. And that goes back to what we were talking about before. If you increase the temperature, there's more vibration in the metal ions that are there, which means it's harder for the electrons to get through. It's not asking for that explanation, but it helps if you understand what's going on. Explaining how the resistance changes. Keep it there, it's explaining, not just describing, so it's not just a case of 1 mark, it gets bigger. So talk about both the axes. As the current increases, the potential difference increases, or you can have that the other way around. The explanation is then that this will then cause the temperature to increase, the wire will get hotter. And as we were just talking about in the previous question, which was a nice little lead into this, if the wire gets hotter, that means the resistance is going to increase. And you can see that resistance is increasing because it's allowing less and less current to go into it, whereas you're still increasing the potential difference. So key 3 bits we're looking for. The current and the potential difference both increase. That means it'll get hotter, which means the resistance will steadily increase. For 5.3, what does it mean if you're more energy efficient? A couple of different things here. So I'd expect you to go for the first bit, which is saying that there's a higher useful amount of energy, or a higher proportion or a higher percentage of the useful amount of energy. I think less people would turn and describe it in terms of power, but you can do where you say there's a higher power output of useful energy, or there's a less wasted power output of energy. If you just put it wastes less energy, it's not in the right level of detail for the demand of the question that we're talking about. So you just need to have a little look at like I was saying at the start of this question, where are we in the exam paper? What level of detail will I need to put in? Talking about some tricky stuff, here comes question 5.4. So we're looking at a light-dependent resistor here. They function very similar to thermistors. Thermistors respond to heat. LDRs depend to light. But the same effect happens. If we had more light, then we would have more current flowing because there's a lower resistance. In this case, it's the other way around. It's saying that the light intensity decreases. So if it decreases, we're going to get less current flowing. That would be on this one, less current flowing, because we'd have a higher resistance. That would then mean that we'd have a higher potential difference. Because the potential difference, the voltage, is going to be shared out across the components. So this one is going to be getting a higher and higher potential difference the more its resistance increases. For question 5.5, what is the resistance of an LDR when the potential difference across it is 4 volts? So, I mean, the simple answer is going from the mark scheme, and we'll start there and I'll tell you where my brain went. So the answer is 1000 ohms. The reason we get to 1000 ohms is looking back at this. If this has got 4 volts, then this one here must have the other remaining bits of the 12 volts, which is 8. So if this is 4 volts and this is 8 volts, this resistance is 2000, so just like this is half the voltage of this one, then this one here must be half the resistance, so it would only be 1000. Where my head went on this one was, right, so there's a voltage, there's a resistance, so we could work out the current flowing through this, and knowing that the current in a series circuit is the same all the way through, we'd know the current of this, we'd know the voltage of this, and then we could work out the resistance of it. So when it says allow a justification using a correct calculation, if you used Ohm's law to do it, you did just as good a job as the first reasoning. Probably just took a bit more time to do it, because that's the way some of our brains work. For question 5.6, calculating the current through the LDR when the LDR's resistance is 5000 ohms. Now, first of all, if you didn't get full marks, it might well be because the resistance in your calculation isn't going to be 5000 ohms. Yeah, I know. So let's go back up and look at why. So in a series circuit like this one here, you've got 5000 ohms here, and you've got 2000 ohms there. So in the circuit, we'll add them together, and that's going to be 7,000 ohms. That might be the first improvement for quite a few of you who thought you did well on this one. So next step when we're looking through at it then, we've got our voltage of 12. There we go, we can write this in. And we're using Ohm's law. We know the current is the times by the resistance to work out the voltage. Let's get my words out. So that's V equals I times R. We've written our numbers in, so that's our first mark in for going for that. We can rearrange it, so we know that the current is going to be 12 divided by 7,000, which is our second mark, which gives us our third mark. 1.71 times 10 to the minus 3 if you want to put it in standard form. If you didn't put it in standard form, that'd be 0.00171. Standard form is easier there, obviously, you see. And it asks it for just two significant figures for the final mark. So you can have your answer as 1.7 times 10 to the minus 3. So with two significant figures are the 1 and the 7. The 1 wasn't significant, and we rounded it down because it was less than 5. Or more likely, I reckon you guys have probably left it as a decimal, so we can round it to 0.0017. Okay. Turning on for question 6. So, 6.1. Looking at smoke alarms of specific use of radiation that we should be familiar with because it's in revision guides and one of our actual required elements to look at. Why does the alarm switch on when the smoke particles enter the plastic casing? Well, the ionizing radiation is creating a current which is flowing across between the detectors. When the particles go in, you can see here that the smoke particles are blocking the alpha radiation. It's not very penetrating. So this short one-word sort of bits is the smoke absorbs the alpha radiation, or the smoke blocks the alpha radiation. Why is it safe to use alpha radiation in the house? Alpha radiation is the biggest sort of radiation, and it's not very penetrating. So it's not going to be able to get through more than a few centimetres of air, and anything else that's there, for example, the skin that's around you. So one mark we're looking for is it's not very penetrating. For 6.3, the smoke alarm wouldn't work with beta or gamma radiation. Explain why. And again, it comes back to penetration. If you put smoke in, beta radiation is going straight through, gamma radiation is going straight through. So they are both too penetrating. There's your first mark. And if you only got one mark, it's probably because you didn't say what the impact on that would be. So if they're both too penetrating, there's going to be no change in the electrical current that's flowing, so the detector wouldn't pick up any change at all. For question 6.4, it's unusual here that we're not actually calculating a half-life. It says, explain why the radiation source inside the smoke alarm should have a long half-life. And it's not just so it can last longer. We need something specific here. They've given you the graph. So let's look at that graph and let's give you a reason why. So you could say a long half-life means the count rate is going to be constant or steady, or the alternative, a short half-life then would mean that the count rate would quickly decrease and then you'd have to keep buying new smoke detectors. So at which point is it useful? Up to about 80 counts per second. So that's going to be 1.3-ish half-lives. So if your half-life is 5 minutes, after just over 5 minutes, it's now going to be a useless device. So we're going to want that half-life to be a decent amount of time. How often would you like to buy a smoke detector? Once every 10 years? Once every 20 years? So you'd want a half-life of something in that sort of a region, and it nicely clearly labelled. For I'll just move the mark scheme down there just in case you need to pause the video and look at it, but it does say that 1.3 half-lives above 80 counts per second. 6.5, ideal properties of using radioactivity inside the body for this sort of detector. So, could you use alpha radiation? Of course you couldn't. It's not going to be penetrating enough, it won't get out of the body. Could you use beta? It's probably going to get damaged by, blocked by pretty much everything in your body. So we're going to want something highly penetrating. That's going to be gamma. The other reason we probably want gamma radiation as well, if we put alpha inside the body, it's highly ionizing, it's the most likely to cause cancer. Beta's less so, but again, it's not particularly well suited because it's not penetrating. So again, we come back to gamma radiation, which has got the lowest ionizing potential, but also the highest penetrating potential. Okay, It's only worth 4 marks, this one, but there's still a quality of written communication. So we want it nice to be logical, clear, capital letters, full stops. Oh, bet you're loving this and looking forward to question 7 now, so let's not disappoint you. So here we go, question 7. We're looking at pressure, obviously. For the first one then, repeat readings would make things more accurate. This is from the first bit of your revision guide, which people quite often look through and skip over. These keywords and how you do science are really, really, really important. Things like accuracy, precision, reliability, validity. Here we go, the word is accurate. So accuracy is how close something is to the true value. So if you're doing repeat readings, the reason you can get closer to a true value is, first of all, you can identify any numbers that don't fit. So if you've got like 10, 10, 10, 10, 10, and 32, 32 doesn't fit, you can discard that. So you can identify and remove anomalies. And then if you did have like 10, 11, 10, 11, 10, 11, 10, 11, you could then average them out to get an answer which is closer to the true value, which may say be like 10.3, which you were never measuring, but you constantly got either side of. It would also reduce any random errors that you got because of measuring equipment. Random errors are easily explained when we look at 7.2. This is a source of a random error. There's 1 mark for it. The particular sort of error that it's called is called a parallax error, and it's caused with things like measuring cylinders or thermometers when you don't read them at eye level. So if you look from above, you get one reading. If you look from below, you'll get a different reading, and if you look straight on, you get another one. So the reason this is called a random error is because there's no guarantee that your eye would be in the same position each time. You could possibly get a little cheeky mark. You could say that it's a systematic error for a mark, and if you explained that if you systematically looked at it from the same angle, for example, from above, you would then be off by the same amount each time rather than being off randomly each time. Still worth correcting to the actual correct answer for us and not risking it because there's no biscuits. 7.3, if you're compressing the gas quickly, it'll get hot just like when you pump a bike tyre. So explain why that would affect the pressure. So if you increase the temperature, that's going to make the particles move faster and have more collisions, which is going to increase the pressure. So let's have a little look at what we're supposed to say. Increase the pressure. Super, just said that. And that increase in pressure is because a higher temperature would mean the particles have more kinetic energy or move more. Okay. Notice the terminology that it's looking at there. It is saying kinetic energy or speed. It's being quite specific. So try and keep it to that sort of vocabulary as well for me. On to 7.4. So depending on who taught you this one, it depends on what you're going to be doing in terms of the calculations. Myself, so looking at what they did, when they're working out this, you've got to assume temperature's constant because, as we just said in the last question, if temperature changes, the pressure changes. Right, so if we've got that as an understanding, what they work out in their calculation here by getting the number of pascals and timesing it by a volume is something equivalent to working out a number of moles. And then when they get that same number of moles, they can then know that the pressure times by our mystery volume would be the same answer as that or equal to that, and then they resolve it. Let's look at it a slightly easier way. So if I was teaching this, I'd say that the pressure of the first system times by the volume of the first system would be the same as the pressure of the second system times by the volume of the second system. So that would be P1 times V1 equals P2 times V2. So in this case here, you could then take the pressure of the second system back to the first side of the equation, and then you'd be able to work out what the missing volume was. It's very, very similar to how you do titrations with C1 times V1 equals C2 times V2. If you do need a little bit of a show and tell for that bit, just call me over in the lesson. I'll come over and help you out with it. For question 7.5, the internal energy of the air increases. So internal energy is both the kinetic energy of the particles as they move and the potential energy that can be added to or removed when you're going through a state change. This isn't going through a state change, so we're talking about what's happening to the particles. So the first thing is the internal energy is changed because we have some work done. Work done is energy transferred. There's your first mark, and I bet a lot of people probably didn't put that. What mark that you probably did get is because the temperature increased which means then you could also say that the kinetic energy of the particles also increases as well. Well, you've made it this far. Give yourself a little pat on the back, smile, look around the room and see if anyone else is doing that yet. Question 8 then. We're looking at comparing shale gas and nuclear power. They put this in because this is the sort of thing which is in the news and appearing in things like Blackpool, where they've got earthquakes happening because of this fracking that's going on. This question asks specifically for the advantages of nuclear power. So if you're not saying why nuclear has an advantage, you're not answering the question. I don't want to hear about bad things about nuclear. I don't want to hear about good things or bad things about the shale gas. So nuclear is good because it doesn't produce carbon dioxide, because it's not burning anything. That then means that it doesn't contribute to the greenhouse gases which are causing global warming. The other advantage, which links into a comparison directly to shale, is that nuclear power doesn't cause earthquakes. The last thing that you can say is something that's not in the question, which would be a really good thing to know. Nuclear power produces an absolute ton of energy. And nuclear power can use a very small mass of fuel, like 1 kilogram of fuel could provide enough fuel to keep entire cities going for a year. Whereas shale gas doesn't do anything near as good as that. So per kilo, it's just far more efficient. For 8.2, the fuel that's used in nuclear power stations, I'm expecting you to do uranium because that's what I'll have taught you in the lessons, but you can also mention about plutonium. 50 points if you said it's uranium-235 instead of the uranium-238. To describe the process of nuclear fission then. So, you'd be saying that a neutron is absorbed or is shot into a large nucleus. I'd be talking about uranium, but you might be talking about plutonium, so we'll just say shot into a large nucleus, like one of them. That nucleus then temporarily gets too bigger, so like uranium-235 will turn into uranium-236. That larger nucleus splits into 2 smaller daughter nuclei. It's not the same each time. It could be a range of different ones. It's hard to predict. When they split, they also release some energy. Some of it's gamma rays, but a lot of it's thermal energy, which we can then trap and use to generate electricity. As well as the energy, we're getting 3 neutrons, or 2 or 3 neutrons, depending what the products are. They conserve the mass. So the very quick bullet points would be a neutron's absorbed. That then makes the fuel split apart. It releases energy and a couple of neutrons at least. Next one is question 9. Getting towards the back end of the paper here. You must be getting pretty excited. So the risk of having an electrical cable touching the metal case. Don't just say you might die. But the easy answer, because it is the first part of the question, even though it's at the back of the exam, is that there is a risk of an electric shock. Anything with a metal case needs to have an earth wire. If it's got a plastic case, it'll just have a little plastic third prong, so you can open the plug properly. But if it's got a metal case, that third part of the plug must be an earth wire, which allows the dangerous current to flow to earth if there is a short in a circuit. For 9.2, the power output of the coffee machine is given to you along with the voltage. That should be a clue that we're going to work out the current. So power is the current times by the voltage. So write out your formula. There's the power, there's the current, there's the voltage. Where did we get 2,530 from? Well, we just converted the kilowatts into watts. So have a mark for writing out the numbers. Have a mark for rearranging it to find out what I is. So we know that 2,530 is the result of getting I and timesing it by 230. If we divide that number by 230, we can find out that I in the first place was 11. That's 11 amps. And think this is a regular household appliance. It's heating something up, so it'll be on a 13 amp fuse. So 11 amps is a really sensible amount. Anything heating stuff up in your house is probably going to be something under 13 amps, unless it's something really major where it'll have its own proper separate electrical supply. 9.3. This is 5 marks for a calculation because it's got 2 formulas in it. Any really high scoring marks with calculations is going to involve changing formulas, significant figures, and multiple formulas. So which ones stand out for you? As soon as we see a change in temperatures and some specific heat capacity, we know we're going to be doing that the energy is the specific heat capacity times by the mass times by the change in energy. Ooh, what am I missing from that equation? Well, the mass, of course, because I'm trying to work that out, but I've not got the energy in the question. So before I can do the specific heat part of the question, I need to find the energy. The other information it gives me is the power of 2.53 and the time of 14 seconds. Now, what we need to know there is that the energy is the power times by the time. So we can get the first part of the equation here. That's the power. Notice we've turned it into watts, not 2.53, 2,530. Times it by the time. It's given in seconds already, don't need to change that. That means in those 14 seconds, it's transferred 35,420 joules. Okay, we can then take that energy and put it into the specific heat capacity equation I mentioned a minute ago. So there's the energy, is the M times C times delta T. That is the energy is the mass times by the specific heat capacity times by the change in temperature. So if we had M and times it by 4,200 and times it by 70, that would equal 35,420. So to find out what M is, we get that 35,420 and then undo what we did. Divide it by 4,200, divide it by 70, and that should give us a mass of 0.12 kilograms. Does that sound sensible for some coffee? Yeah, it does. Okay, you don't make kilograms of coffee at a time, do you? Well, no, okay, normal people don't. Question 10. Here we go. So we're looking at the mass of air going per second, and this is just look at the information that's in the question. We're getting 2.3 times 10 to the 4. That's like 23,000 cubic meters of air passing each second. And each one of those is 1.2 kilograms. So we're going to literally times those together. It's 1.2 times the 2.3 times 10 to the 4, or times by the 23,000. That'll give you a mass of 27,600. And if you kept it in standard form to begin with, then the answer would be 2.76 times 10 to the 4 in the calculator. Because those numbers there are rounded to two significant figures, it means the answer can also be in two significant figures as well as 28,000 or 2.8 times 10 to the 4. Okay, regardless, you'd get the mark. For part 2, it says the power output of the turbine is proportional to the kinetic energy in the air passing it. Describe the effect of the power when the wind speed is halved. So remember here that kinetic energy is a half times m times v squared. Okay, so if you halve the wind speed, then you're going to halve the mass. So that's going to decrease by a factor of 2, because if you've got half as much air, then you have half as much energy. But when you've got the wind speed being halved, it's the v squared which is affecting the energy. So it's not just that you halve something and then it'll halve the output. You're going to half it and half it again. So you're going to divide it by a factor of 4. So kinetic energy is going to decrease by a factor of 8 overall because you've halved it, because there's less mass going, and you've divided it by 4 or you've quartered it because you've got the v squared having a bigger impact on it. So combined, you're going to have it decrease by a factor of 8. Quite a difficult question to explain, in my opinion. So if you got that wrong, don't kick yourself. And if you need help with understanding the maths again, pop your hand up, ask me to come over, and I'll give you a hand with it. For 10.3, we're calculating the speed of air passing the blades each second. We're given the power of it, and we're given the mass of it. Okay, so the kinetic energy is a half times m times v squared. You might be asking, where's the energy? Well, it says we've got 388 kilowatts. That is 388 joules per, 1,000 joules per second, and it wants to know how much is happening per second. So that number there, 388 kilowatts, is going to be 388,000 joules per second. So let me just move my mark scheme down so we can catch up to where I'm talking about. So that's where this number comes from. The kinetic energy is a half times the mass times the v squared. So 388,000 is the joules that we just worked out. A half times it by, so is equal to a half times by the mass, which is given to you here, 13,800, times by v squared. We don't know what v squared is. Okay, so if we got v squared and timesed it by these two numbers, we'd get 388,000. So if we got that number and divided it by a half and divided it by 13,800, we'd find out what v squared is. V squared is 56.2. Pop that into your calculator and square root it. We find that the velocity is 7.5 meters per second. It does say in the mark scheme that we're looking for an answer that only rounds to 7.5, otherwise it's not being accepted. That then, last question on the paper. You can see why, it's been nice and tricky for you. Now that you've gone through it, look at the areas that you need to do some improvements on. Look at doing some improvements using revision guides, Seneca, Tassamai, even just planning for what you're going to come and do in revision sessions after school or before school. Okay? Well done, ladies and gents. Please make sure you've done your corrections in red pen.